Okay, I think people are starting to come in. Welcome, everyone. My name is Mark Brown, and welcome to our last session for PAS Summit. So if you're here, thanks for joining us and sticking around. This session is how to model and partition data for Azure Cosmos DB, Microsoft's distributed NoSQL database for infinite scale. So my name is Mark Brown. I'm a program manager on the Cosmos DB team. I'm joined by my colleague, Gary Hope. Hi, Gary.
Hi, all. Happy to be here today.
Gary's going to moderate the chat or the Q&A for our session today. And if you have any questions during today's session, just feel free to ask them at any time. We don't need to save questions for the Q&A at the end. So if you've got a question on your mind, feel free to type it in there. Gary will just chime on in and interrupt me, and we'll take your questions as they come in.
Look forward to seeing you all in the questions.
Yep. Let's see, a little about me. I'm been at Microsoft for a little over 20 years now. Done a lot of different things over those years. Started off in the Windows mobile space. I've worked on developer security, Bing Maps, Virtual Earth as it was known back then, and web space as well. In Azure, I've worked on our app services, Redis cache, networking, and I've been on the Cosmos DB team for a little over 3 years now. And I have to say, it's probably the most fun I've had since being in Azure. Building and working on a distributed NoSQL database is a heck of a lot of fun. So let's go on. So what is Azure Cosmos DB? Well, officially, it's Microsoft's NoSQL database on Azure. Well, what do we mean when we say NoSQL? Well, NoSQL databases are basically non-relational databases, and they're also horizontally scalable. So let's talk about some of the horizontal scale aspects of Cosmos DB. Unless your app or your database is really small with just a little bit of data, request and your data is likely going to be stored on a number of different physical servers or partitions within something we call a container. That's kind of a logical wrapper around these physical partitions that we store your data in. Now, in Cosmos, we abstract all this out of the way. But under the hood, you're reading and writing data in and out of Cosmos across this cluster of servers. And this is better known as a scale out, and it's how we achieve horizontal scalability by enabling unlimited storage. So when you need more storage in Cosmos, you just keep writing more data. We simply just add more servers or partitions to the cluster. The other nice thing about this as well is it provides unlimited throughput because each server we add has its own compute. It's got its own CPU, its own memory, its own I/O, its own NIC. So this adds that additional capacity to handle the request for when you need it. Now, Cosmos DB is also non-relational. Now, when you work with relational databases, you of course have the ability to define these constraints between the different entities or the tables that you're storing the data in. And this just lets you define things like foreign keys between these different entity types or perform joins across these different entity types. A relational database, or excuse me, a non-relational database like Cosmos DB, we don't implement any of these types of relational constraints. Now, you may wonder why. Well, simply put, because Cosmos is horizontally scalable, we're a scale-out database, and we use lots of different servers to store your data. Because that data is going to be stored on all of these different servers, it's just not something that we want to do from a kind of a performance or availability standpoint. Now, I don't want to suggest that it's impossible to do these types of things. In fact, some databases will put like locks and latches for data that's stored across different servers. But because Cosmos DB is designed to provide predictable performance and high availability, it's not something we want to implement that would jeopardize those types of performance guarantees that we want to provide. Can I see number of attendees? I cannot. I have no idea who's here. So hopefully you're here. If anyone's here, please say something in the chat so Gary knows that there's someone here in our session. Okay, so you may be asking yourself now, because we don't implement any of these relational constraints or these other types of things that you would use to maintain your ACID semantics, Is Cosmos good for relational workloads? And the answer is absolutely. Of course it is. I wouldn't be here if it wasn't. Most workloads on Cosmos are, in fact, relational. You just need to learn different techniques to implement the relationships between your entities. And I'm going to show you those here today. Now, this approach is very different than designing a data model for a traditional or relational database. And if you're new to this type of database, I would not follow what you think your intuitions would tell you when designing a database for something like Cosmos. This isn't really very intuitive, in fact. And in fact, kind of best practices in a relational world are somewhat of an anti-pattern for how you want to model and design a database for a database like Cosmos DB. Okay, so let's put this into practice. I'm going to spend the rest of the session, and we're going to take a relational database that I think most of you would be familiar with, at least for those from SQL Server world, which I guess maybe everyone here. We're going to take a subset of the AdventureWorks 2017 database that you're looking at here. And these tables kind of represent for us kind of the canonical workload. And let me go through these. So we've got a customer table here, and then it has a one-to-many relationship to customer address table. There's also customer password. So there's a one-to-one relationship between our customer entity and customer password. Next, we've got our product table. So we've got the product table there. It has a many relationship or a one-to-many from product category to product. And then you've got product tag. And then within product tag, you've got a many-to-many relationship persisted in our product tags table, where we've got multiple products and multiple tags and the cross product of those there. And then finally, we have our sales order and sales order detail and a one-to-many relationship there, and then a one-to-many relationship between customer and sales orders. Now, with a non-relational document database like Cosmos, there isn't much we can do with this. We would never use these tables as is because the cost and performance for trying to perform those same operations would be excessive and prohibitive, in fact. And I'm going to show that to you as we go through our modeling exercise here. Another thing I want to point out, too, is that in the relational world, the relationships between the data are very important for modeling the database. For a NoSQL database like Cosmos, this is only part of the story. You start with the relationships. They, of course, still matter. Relationships between data matter no matter what kind of database you're using. But what's most important for a database like Cosmos is the access patterns for that data. And as I go through the application or I go through this exercise in this talk, I'm going to show you how those access patterns influence the decisions we're going to make as to how we want to model our data, as well as how we want to partition it as well. All right, so what's going on with my slide here? Slide is not advancing. There we go. Come on. Oh, it is working. Sorry. Oh, okay. Build slide here. Oh, let's just go through these. Okay. All right. So let's talk about the operations for our application here, because this is where I'm going to spend a lot of time as I go through each of these things. So a real e-commerce application would obviously have to implement lots more requests and different types of things. But I think this subset that we've got here is a good way to illustrate kind of those things that we're going to do. So we're going to create and edit a customer here. We, of course, want to retrieve a customer. We're going to create and edit product categories, list all categories, create and edit tags. We're going to list those tags, create and edit products, and then list all products from a category. And then we want that category name in there too, and I'll explain why that's important. We also want to create a sales order, of course, for an e-commerce application. We want to list all sales for a customer. That's an important operation. If I'm a customer and I log into my e-commerce app, I want to be able to go and see my past orders. And then I've got another one in here that's a little different. I want to query my top 10 customers by the number of sales orders. So let's just say I've got a kind of a frequent flyer type of thing, or my top customers, and I want to send them a little gift or a gift card or something like that. How do I figure out who my top 10 customers are so I can send them their little gift? So we'll use that query there. It's kind of more of an analytic type query, and we'll show you how we model and handle that type of thing here. Okay, so let's get started, and we're going to remodel our relational database, AdventureWorks 2017, in Cosmos DB. And let's get started with our customer entities here. So we've got these three tables, customer, customer address, and customer password. First thing we need to do is we need to translate these into JSON. Cosmos DB is a JSON store. So of course we want to take our tables from a relational world or a SQL world and then represent them as JSON within here. Next, we want to embed our address into our customer table. So JSON, of course, we can store hierarchical data. We can embed data like an array or another object within there, and we're going to stick it inside our customer table. We're also going to do the same with our password data, and we're going to embed that as an object inside our customer table. And the reason we want to do this is because the thing that's important to us here is we want to get data as efficiently as possible. And if I store this data in 3 separate containers, I've got to make 3 separate requests to get it. Because Cosmos DB allows us to store this hierarchical data and different schemas of data inside the same document, we're going to embed it because now I can get all of the information for this customer in a single request. This is both less expensive and better on storage. Okay, so, excuse me. Any questions? No. At this point, people ask, so when would I embed data versus when would I reference it? And there's actually some hard and fast rules around when I would do this. You would embed data typically when you have a one-to-one relationship. Our customer and customer password entities would fit that bill there. Or if it's a one-to-few relationship. Now, you may be asking, one-to-few, what does that even mean? It's a one-to-many relationship, but it's a bounded relationship. Customer address would be a perfect example of this. You can have a one-to-many relationship between customer and customer address, but you don't have an unlimited number of addresses, right? You typically, in an e-commerce application, would have a handful. You would have yours, your mom's, your brother's, your kids, whatever. It's just a few of them, right? So it's a bounded set. There's some kind of limit to it. The other rule around this is that the related items are either queried or they're updated together at the same time. Now, you want to reference your data when it's a one-to-many relationship. And here I mean strictly one-to-many, especially if it's unbounded or extremely large. A good example here would be, say, a blogging platform. I would model my data such that I would have one document for my post that would be within my container. And then for each comment that's in there, I could, if I wanted to, embed that inside a comments array inside that post document. But if I had a post that had thousands or tens of thousands of comments on it, I'm going to quickly blow that up. And there is a limit to the maximum size of a document within Cosmos DB. That's 2 megabytes. So for that reason there, when you get into these unbounded or very, very large one-to-many relationships, you want to insert that other data as another row inside that container. And then you can reference it within, like, say, a query or something. The other is many-to-many relationships. Now, our product tags table, where I've got many products and many tags, this is another one where we want to add this and do it as a reference. And I'll show you later on when we get to the product tags how we handle that kind of situation. The other scenario, too, is when the related items are queried or updated independently. In particular, the scenario around updated independently is really important. Within Cosmos, when you do an update to a document, you replace the entire document. So you're going to have a very high, or for large documents and those that maybe are increasing in size, if you have large documents or you update a small number of properties quite frequently, so there's high concurrency on updates to those properties, this can get quite expensive. I mean, you're going to have a lot of CPU usage on your client. You're going to have heavy payloads over the wire, and it's going to be high cost from a request unit, right, or a throughput perspective for Cosmos. The right way to approach that type of scenario, in fact, is if you have a large document or any size document, but you only update a small number of properties and do that with high frequency, is you want to shred that document into 2. And then you basically they're referenced to each other. And then for the document where you're doing high volume of updates, that's a separate document, and hopefully, generally it's a smaller document. And then you would have another document that would have your more static properties there that don't change that much. That way you get higher efficiency in terms of the throughput consumption for the updates, also smaller payload, and just more efficient on the client side. So everything gets a little faster, better performance, lower cost. Okay, so because we have this one-to-one and one-to-few relationship between our entities, we're going to want to retrieve all of this data at the same time with our customer here, of course, right? So when the customer logs in, we're going to check that password. And of course, the customer we're going to need their information there. And of course, if they want to make an order, we need addresses for them to be able to select from. So we want all this information at once. So it makes sense to embed all of this data into a single entity here. So now that we've defined our first entity and we're going to store it in our customer container, we're going to create this new container, and we need to create or you may be asking, well, we need to create a partition key for this container. And you may be asking, well, what is a partition key? Okay, well, before we get to there, let's do a short demo. I'm going to show you querying for each of the individual entities for our customer entities there. And then I'll show you the performance when I do a query for a single customer, or when it's all embedded together in a single document there. So let us go to our other screen here. Okay, so what I've got here is I've got a Cosmos DB account, and I've got 4 versions of our model that are going to evolve from V1, which is essentially a container per entity, which is a very naive and incorrect model for our e-commerce database, and then a V2, which shows our work on the customer modeling that we've done, and then a V3, and then a V4 that has the final model, and I'll show you that at the end. So first thing I want to do is let's measure the performance for our customer logging into our application. So we want to do a query to get all the customer information here. So I've got a query here, select star from C, where C.ID equals this GUID, which is this customer ID, and this is the customer. This is the customer container here, so we'll go ahead and run this. What's this? That shouldn't do that. There we go. Okay, here's our customer coming back here. Not much data. And we want to get our query stats on this. This is the cost for our query. And here you can see it's 2.83 RU per second. This is not rendering weird. This is rendering weird, but that's okay. We've got our value. Okay, next we need to query our customer address data. So that's our next container here. And here's our query, select star from C, where C.customer ID equals that same value. So we'll go ahead and we'll run that query here. And okay, it says it successfully ran, but I don't see anything here. Oh, here it is. Wow, this. Okay, here we go. And here we go. Our RU value is 11. So we had 3 and 11. So we're up to 14 RU here. And query 3, this is our customer password container here. Let's run that query. And there's our customer password data. And we've got 2.83 there. So what, 3? So we had 3, 11, that's 14, and another 3. So that's 17. So we had about 17 roughly RUs per second as the cost for each of those 3 queries. And we had to run 3 queries to do it. So that adds latency to that. Let's go and look at our V2 database. So in our V2 database, you can see, by the way, fewer containers in here, right? Because I've got customer address, and customer password all within my customer container here. So already doing better from the number of containers that I have. And by the way, each container requires throughput if you're using, well, in this one, I'm using shared throughput. But in most cases, you would want to use container level throughput. And each of those has a minimum of 400 RU. So the fewer containers you have, the less expensive your workload's going to be. Okay, so this last query is from my new customer container where I've embedded all my customer data, and then let's run that query. And okay. And here you can see I've got my customer information. So that's the data from the customer container. Here's my addresses, all embedded in here. And then there's my password. So I've got all the data I need, one single request, one single query. And how much did it cost? 2.83 RU. So I've saved a whole ton of throughput or cost for running that query by embedding that data into a single container and then returning that as this JSON object back to the user. Okay, so obviously then embedding your data is going to get more efficiency because you're going to use fewer requests to get your data. And that's a key concept I want you to understand is the operations that you run is really what should drive kind of the design for your data model when you want to embed it, right? Because we're getting all this data at the same time. I want to embed it all within the same container so that I can get it with a single request. The thing to understand that's kind of fundamental with a database like Cosmos versus, say, SQL Server is that when SQL Server and relational databases as a concept were invented back in 1970, the cost of storage relative compute was insanely high. It was expensive, like a megabyte of storage cost thousands and thousands of dollars. Imagine a gigabyte of storage would cost you, I don't know, $1 billion probably back in 1970 if you could even get it. Today, the economics on this thing is completely flipped. The cost of storage is cheap, very cheap, especially compared to compute. So with a database like Cosmos, databases like this came about because you had these cloud scale applications that needed very high concurrency and high availability, massive quantities of data, serving lots of different users all at the same time, scaling to a point where where you could not get a relational database. I mean, for non-sharded relational databases, your maximum size was about 4 terabytes. For a database like this, it's unlimited. In fact, it's theoretically infinite because you just keep adding servers to your storage, and that just keeps adding the storage to your database, and of course, additional compute to handle all the requests. So these days, when you're designing for this type of data store, the thing you want to optimize for is not storage, where you're doing third normal form and reducing the amount of duplicate data. In this type of database, it doesn't matter if you duplicate data. The thing you're optimizing for is to reduce the number of requests to get that data. So embedding data like this into a single document meets that objective where you're going to reduce the number of requests that are going to be made to get that data. That reduces the amount of time, and thus the performance is going to be higher, and your cost is going to be less. Okay, let me show you. Any questions yet? Nope, good. Okay, so that shows you how to run a query using the portal, but you don't use the portal to write your application. You actually use code to do that. So I've got a little app here that I've written. This is all in C# using .NET, of course, and I'll show you how do I query for a customer when I'm writing the application. So here, let me walk you through this. I've got a database object here. This is a proxy to my database, so I'm going to call client. This is my SDK client, and I'm going to call get database. And here it is. This is database v2. That's the database that we had in our new database with the customer, where it was all embedded. Here's my customer container. Here's that same customer ID that I used in my query. So Destiny Peterson, or whatever her name was, it's going to be our customer name. Here is the string for my SQL. So select star from C, where c.id equals @id. That's going to be my parameter here. And then let me show you the code for how do I define a query with a parameter. So I've got my container, and then this function, get item query iterator. I'm going to create a new SQL definition, pass in my SQL string, and then create a with parameter in my build statement there, defined as @id, pass in my customer ID. I'm also going to pass in the partition key because we're partitioned and by customer ID for this container. So for that, I want to, and I'll get more into this partitioning later, but I wanted to show you this code first. But we're going to pass a partition key because that's going to help route where we're going to find the data in our database. So, and then when I get that query or get that result, I'm going to loop through it, and I'm going to print it out, and then I'll show you the request charge for that as well. So let's run this query. Query for a single customer, number A. And here you can see the same data. There it is, Destiny Peterson with her name. There's the address in there. And then there's the password object. And you can see the request charge is 2.83 RU. Okay, so let's go back to slides here. All righty. Okay, so we talked a little bit about, let's advance slide here. Here we are. Okay, so let's talk about partitioning. I kind of teased you a little bit about partitioning before we went into demos, and then of course into the demo itself when we were passing the partition key for our query. But remember earlier when I referred to Cosmos DB as a container and an abstraction over these physical servers, right? This cluster of physical servers. Well, when storing documents in a Cosmos DB container, these documents end up being dispatched to these different physical servers. So the question is how do I decide that this document should go here and that document should go here and this one goes there? So technically, we're not really assigning documents to servers. Instead, these documents are being written to these things we call logical partitions. And it's these logical partitions that sit on the physical servers. So from a user perspective, you don't really need to care too much about the physical servers when you're designing your data model. You just need to care that your data is getting written to these different logical partitions. Okay, so how do I decide which logical partition my document should go to? Well, that's where the partition key comes in. Excuse me, I'm gonna have a little sip of coffee. When I'm creating a container in Cosmos DB, I need to define the partition key, which is a property in every document, and it is used, the value of that is used to decide which logical partition my data is gonna sit on. You can think of it kind of like an address to route your data to. Now, using the example of a username for my partition key, we'd end up with logical partitions where username equals Andrew, or username equals Deborah, or username equals Mark, or Theo. So each of the documents with that partition key value end up on those logical partitions that correspond to it. Okay, so let's talk about some constraints here. I already mentioned earlier that each document has a maximum size of 2 megabytes, right? So remember, on our discussion about embed versus reference, this is why you don't want unbounded arrays inside your documents, because if you get to that 2 megabyte limit, you're going to start throwing exceptions in there and you won't be able to take any more data, write any more data into that document there. And of course, it's not efficient when you have an ever increasing document size when you're doing updates on it. Excuse me. As the document grows larger, the amount of throughput necessary to do updates or do operations on it gets much greater. So it's better, more efficient to work with lots of smaller documents in general. Particularly if you're doing lots of high concurrency or have high concurrency in your application. The other thing you need to understand is that each logical partition has 20 megabytes or 20 gigabytes of max storage. So you can't have more than 20 gigabytes of documents where, say, the username equals Andrew. Okay, so when working with data, one thing you want to try to achieve, in fact, a major objective of this thing when you're writing data across these partitions, is you want to make sure that you get an even distribution of your data as you write it into your database. When you don't get that, this is what we call a hot partition, and it's something you very much want to avoid when you're designing your database. The same goes for requests as well. If most of all of your requests are hitting the same logical partition, then this is going to be a bottleneck that's going to drastically limit the overall scalability of your model. One thing to kind of keep in mind in here is that we want to end up with this design is that where your storage is even across all of your logical partitions and thus the physical partitions behind it. And then the same with the throughput in here. Now, let me just spend a moment kind of talking about this. So when you, and maybe I've got this on a, well, let me show you. Let me go ahead a little bit here. Let me show you this first, and then I'll get kind of to a meta point I want to make here. So we talked about this even distribution of storage and the throughput in here. So let me take an example here. So if I have a query and the filter predicate on that query is username and I'm passing in Mark, This is a good partition key, obviously, or in a good use of it with this query, because when I make a query like this, it's going to go to a single logical partition and thus go to a single physical partition. And this is a good thing. We're not going to have what we call a fanout. Now, a fanout is going to look like something like this, where I've got a filter predicate that's not using the partition key. And in this example here, I'm using favorite color. And the problem with that is that I don't know where to route that query. I've got to hit all of my logical partitions to go find that data and all of the physical partitions behind it. So let me talk to you about the kind of mapping of the physical to the logical and why this even distribution of storage matters. Now, from storage, it's easy to understand. There's a maximum limit on storage. You've got 20 gig for logical partition. So you want to have kind of a good even spread of that, but also you want a good high cardinality in your partition key as well, such that you never approach or get to that 20 gigabytes. So even distribution there. You can also apply a TTL to your data and also kind of avoid that. But let's just say that, in the absence of that, you need that even distribution so that you're writing data out with high cardinality across those things. You also, the other thing to keep in mind is when you provision throughput, this throughput is evenly distributed across physical partitions within your database or within your container. So if I end up with a scenario, let me go back, and back. So assuming I've got 3 physical partitions behind here, and I've got request, and the throughput for that is evenly distributed. So I'd have, say, 30,000 RU. I've got 10,000 RU for each physical partition, which is the maximum amount of throughput I can get on that partition. And I've got a bunch of requests that are all hitting one partition. 2 things are happening. One, I'm not getting the full 30,000 RU because it's attached to each of those physical partitions. So I'm not using all the throughput I've provisioned. I'm not being efficient with it. The second thing is if all my requests are going to a single physical partition, I have underused partitions where I've got this throughput that I'm paying for. So it's both bad from a performance perspective, but it's also bad from an efficiency and cost perspective. And what we see in scenarios where people have something like a hot partition like this is they notice that their latency is bad, which I get it because they're only using a low number of the throughput that they provision. So what they end up doing is they end up provisioning more throughput. Well, that doesn't always really work because you may still have the same problem hitting the same physical partition depending on the logical partition key. Because when you do add more throughput, we will split those partitions and relocate them on the new physical partitions, but it may not fix the underlying problem there, which is you've got this hot partition. The other problem as a result of that is that people say, whoa, it's super expensive. Well, of course it's super expensive because your design is not very good. You're not evenly distributing that throughput across all of those different partitions, which is kind of the objective when you have a scale-out database. Same on the storage side. So one of the mistakes I often see from people is they will use date as a partition key. And I get it, it makes sense. Usually data is timely, if you will, right? It's temporal. You want data that's generally, the newer the data, generally the more interest or the more queries and the more operations that happen to it. However, and what's interesting for date is when you use date, if the amount of load or request is typically even across days, then you will look like it's a good partition key from a storage perspective because each logical partition will have the same amount of data. However, from a request standpoint, it's a terrible choice. And the reason is because all the requests are hitting that same logical partition because it's the current day. So that's a terrible partition key to use. It's something you should try to generally avoid. You want to find something else that's going to help spread that load across all those different partitions, but maybe have date as a part of that. You could maybe do a synthetic key, or we have this new thing called hierarchical keys, something else that's going to help spread that load there. The other thing too is from a query perspective, and I kind of showed this earlier, right? You want to try and design where your writes are going to spread the load across a wide range of partition keys, but you want to answer queries using a one or a bounded number of partitions. You want to avoid this scenario here where I'm fanning out to all of these different partitions here. This is expensive, it's slow. You really want to get to a point where you're using this. Now, I understand that it's somewhat, not just counterintuitive, but you're kind of asking for two opposites at the same time. I want to spread that load across a lot of different partitions, but I want to also design it such that I'm answering queries with a single partition. There's a trade-off in some cases. If you have a write-heavy workload, then the former is what you want. You want to spread that load across that. If you have a read-heavy workload, then this is kind of what you want here. If you have a workload where you have to satisfy both, you would use something called change speed, which I'll show you a little bit later. And what you would do is you would ingest that data into one container that's optimized for the writes, and then use change speed to essentially copy that data into another container that's using a partition strategy that's going to be used to serve queries on there. And you can have one maybe for one set of queries and then another for another set of queries. It's generally okay. Again, we don't care really too much about copying data because the storage is cheap. What we care most about is what is the most efficient way of designing our database to handle our workload, and understanding those patterns on the read patterns and the write patterns into your database and the volumes, the relative volumes of those things, because there is a cost associated by creating a second container or a third container and then using change speed to copy all new data each time it's written or updated into your first container into second containers. And part of the process of designing an efficient workload in Cosmos DB is figuring out what is the relative cost of doing each of these things. And so understanding, again, those access patterns, but not just that, the volume of those access patterns or those operations that happen is going to be part of the process as you're designing your database for Cosmos. Now, you can't always get it right, and you will make multiple iterations on this thing, but I just want to prepare your brains or your minds for this is kind of the process and how it works for a database like Cosmos. So, okay, spent a lot of time working there. I hope I'm staying on schedule. Let's keep on clicking through here. Okay, so we just talked a lot about partitioning. I hope you have a good grasp on partitioning and why it matters so much. It is absolutely critical to your ability to scale, to use a partition key that is correct and efficient, because it's not just the scale, it's the efficiency as well. So with all that knowledge now, we need to choose a partition key for our customer container. Now, let's go back and look at what are we doing? What operations are we doing here for this container? We're going to create a customer. We're going to edit a customer. We're not going to do those operations very often. You're going to create a customer once for that customer, and you may edit the customer every so often. The operation you're going to do the most is we're going to retrieve that customer. And not only that, but you're going to retrieve it by their ID, right? And that may be the ID that they used or an email address or something that's unique. But whatever it is, that's the thing you're going to partition by. So we're going to call, since we're using ID here in our scenario here, we're going to use ID as our partition key for our customer container. Okay, so this should make a good, suitable partition key for our container. Now, one thing I want to call out here is when you use ID as the partition key for your container, you are going to end up with as many logical partitions as you have customers within your database. Some cases, people will freak out and they say, hey, this doesn't feel right to me to have all of these different logical partitions. Is this the okay thing to do? And the answer is yes, it's okay. Logical partitions are a virtual concept. They don't matter in terms of how many you have. You can have an unlimited number of logical partitions. In fact, when you have a partition key that's of ID within a database like Cosmos, you've functionally created kind of a key value pair, a key value data store with Cosmos DB. Cosmos is going to co-locate all those logical partitions on the underlying physical partitions, and they move them around as necessary in there to make sure that there's the right amount of storage within them. So no need to worry about it. It's okay. No upper limit. You can have as many as you want. Okay, let's do another demo here. In this one, I'm going to show you one cool thing when you have data where you know the ID and the partition key for your data, and that is called a point read. So why is this not working? Whoops, hold on. I used the wrong key. Here we go. Okay, we're back at our app here, and I'm going to show you a point read. And here I've implemented it as get customer within my little demo app here. We're going to do the same thing again that we did with the query. We're going to get our database reference, our container reference. I've got my same customer ID, and I'm going to create or write out what's called this function, read item async. Now, read item async takes precisely two different values. It takes the ID for the document, and it takes the partition key. And in our scenario here, that's the same data. Customer ID is we're partitioned by ID, so we're basically passing customer ID for two different values there. And once I get that, I'll print that out, and then I'll show you the request charge on that. And let's show you that. So that's number option B here. Okay, so let me do this. There's our data, same customer, and look, our point request charge for that point read is just a single RU. That is very efficient. Remember before we had, what, 17 RU, 3 different operations to get all of that data. We've embedded it all into a single document. We did a query for it earlier that was a little less than 3 RU, but I can get even better efficiency if I do this point read and it's a single RU. Now, you may be asking, how can I make that, how can that be so efficient within there? And the reason is because a point read, these types of operations go around the query engine. There's no interpreting your query, creating a query plan, going and fetching the data, and then crafting the response. This operation here goes directly to the backend store. It knows exactly which partition to grab the data from because we passed the partition key in. It uses the ID to go do a lookup for that single document, and then it returns it back, and that's it. So 1 RU to get that piece of data. And in fact, we just want to point out, Cosmos is unique in that it is the only database that provides an SLA on latency. This type of operation, when you're using direct mode, which basically goes directly to the replicas, like we're going here, to get a kilobyte of data is going to be less than 10 milliseconds at P99. And we also will provide a SLA on that latency for you there too. Okay, any questions, Gary? No questions. Okay. Maybe people are just blown away.
I think you're hitting all the marks there, Mark. There's no questions.
That's great. Okay. Well, I hope that's a good thing. Let's go back to slides here. Okay. How are we doing on time? It's almost 2. We're going till half past, correct? I think we're good here on time. All right. So there's customer. We're done with customer. Let's move on. We're going to do our product tables here, and we'll start with the product category. We're going to do the same thing we did earlier, which is we're going to translate this into a JSON document. And we're going to store it in a container. Oh, let's get crazy here. We're going to call it product category. We next need to figure out a partition key for this guy. Well, let's look at the operations we're going to do here. We need to list, create a product category, edit a product category, and we need to list all product categories. So to do that, we'll run this query here, select star from C. But there's an issue here, and I'm going to set this up for you. There's no where filter on this query. Remember before, we wanted to have queries that were going to hit a single logical partition. Well, there's no where filter here, so how do we possibly do that? How do we make this into a single partition query? Oops, let's keep going here. Well, the answer is we're going to use a little trick, and we're going to apply it here. And we're going to give this a new property, and we're going to call it type. And this is the discriminator property we're calling this here. And we're going to give that name, property name, we're going to call it type. And we're going to stick a constant value in there, and we'll set that value as category for all of our different categories. Now, I know that this container is never going to be, even without a partition key, is never going to get to be 20 gig in size, right? So you may be asking yourself, Mark, why are you doing this? This looks rather ridiculous and obnoxious. I agree, it looks rather ridiculous and obnoxious, but there's a reason I'm doing this. And if you just stick with me, I'll explain it to you after I get through a couple other steps here. And then at the end of this talk, I'm going to show you something that maybe will blow your minds. Okay, So let's do another little query here. We're going to query product categories. So let me go back to my app demo here. And here's my function. I'm going to list all product categories, I'm calling it. Here's my database v2, my product category container. And here's my query, select star from C, where C.type equals category. Here's my get item query iterator, my query definition, passing in my partition key. It's just going to be that constant value of category. So I've just kind of hard coded it in here. And we'll just go through and list all the categories that I get back. And do I show request charge? And yeah, I'll show you the request charge too. All right, so list all product categories. That's number C here. And you can see I've got, I think there's about 30 of these things within AdventureWorks. They're all different bike type categories within here. And here you can see my request charge is just a little over 4 RU for this. So that's okay, good efficient query there for that. It probably would have been the same had I just done select star from C. But like I said, just stick with me, I promise that this will make sense. Okay, let's go back to slides. All right, so next let's look at product tags here. So I'm going to apply the same process. We're going to put this thing in a JSON document. I'm going to stick it in a container called product tag because I'm crazy like that. Next, we need to figure out same access patterns, create a tag, edit a tag. I'm going to list all product tags. We're going to apply the same trick here, which is I'm going to create this discriminator property called type. And I'm going to have a constant value tag in there. So we're going to do the same exact thing that we did with our product category. Okay. Next, let's look at the product table in here. So I want to take a look at the relationships in here, translate that into JSON. And we can see that I've got this many-to-many relationship with tags in here. Now, I need to access the product tags in my application, meaning that when I display the product, I want the tags to appear as well when it shows up on that product tag. I may also, at some point, maybe want to query using product tags as well. Now, I could handle this where I want the tags to show up with the product in one of 2 ways. I could store my product info in my product tags, or I could materialize those tags inside my product table. Now, given that there's much fewer tags for product than product for tags, it makes more sense to just embed and materialize those product tags and embed them inside my product table. Remember too, there's this one-to-few relationship between the product and the tags. So this makes it actually a pretty fair candidate for embedding inside my product table. So here you can see I've got my tags as an ID or as an array within my product table. I'm going to store that in a container called product. Next, let's figure out a good partition key for this guy. We want to look at the operations on here. Of course, I want to create a product. I want to edit a product. But the operation we need to work here or do the most that's going to be very often run is we want to list all products from a category. And not only that, but we also want to show the name of the category within there and all the tags. So this is going to be our query. Select star from C, where C.category ID equals, say, category A within there. And so in order to make this a single partition query, then it makes sense then the category ID should be the partition key that we use in our product table. And it will make a good partition key for us here. However, we've got a problem. I cannot just have the category ID in this table and the category or in the tag IDs. This is a problem in that I need to display this category name when I display my product and when I request that. And I also need to list all the tag names. I mean, does it make sense just to have category ID and tag IDs show up on my product page? I need to see the names of these things. So how am I going to do that? Well, we're going to run our first query, right? We need to run that just to get the product data back. But then I need to get the category name. So after I get my products back for that category, I need to go get the name of the category. So I got to then query my category, my product category container here, right? And then each product that comes back, right? Because I'm going to have multiple products when I run my query. by category, right? So I could have one or more products within there. Each of those products is going to have its own set of tags. I mean, they may have the same tags, but they may have their own set of tags as well. So for each product that comes back, I then have to run this query to get each of the tags back. So I've got to run as many products as I get back. I've got to run that tags query for as many products as I get back. Now, you may be asking, hey, well, why not can I just use joins in here? Well, remember, we're a NoSQL database. We don't implement joins. We're non-relational in that sense. So you can't do these types of things. Data needs to be modeled such that it's going to be available when you need it in your request, okay? So what we're going to do here is we're going to denormalize here, and we're going to embed the category name for our product category, and then we're going to embed all the tag names for each of those here. So now each time I run a query by a category ID and get all of my products, I'm going to get all of the data back for everything that I need, and just do it inside a single request. Okay, back to another demo. So this time we're going to do a query on a product with a category name and get the category name back and all the tag names in here. All right. Right, so I'm going to query products by category ID here. And so now we're on to our V3 database because we're working on our products within here. So I'm getting a reference to my V3 database, and then my container is, of course, going to be product. Now I'm going to run this query. The category name I'm going for is components and headsets. Here's the category ID. It's just another GUID that I'm passing in. Here's my query, the one I showed you earlier. So select star from C where category ID, C.category ID equals that category ID. Here's my query definition, my parameter, my partition key that I'm passing in. That's the category ID again, of course. And then we'll iterate all through those and show the request charge. All right. So query products by category ID, that's option D here. And this is components and headsets. And let's see how many I got. I got 1, 2, 3 products in that category. And here you can see, here's the category ID that I passed in. There's the category name. There's the SKU, there's the name, there's the description, there's the price. Here's the array of tags. I've got tag ID, but I've got the tag names in here showing up. So I can display those on the product page. If this was a real database, I'd have probably the image of the thing showing up as well on the product page, but I'm just showing this in a little console app. Here's our second category. So, same category name, product name, tags, and then our third product, same thing again, different tags in here. Best of all, here's our request charge, 2.91 RU. Very, very efficient. There's no way we could do this if we were having to go and run multiple queries to go get all this stuff back from all 3 of those different containers. So again, we're embedding our data in here, denormalizing, putting that data all together, and then getting it back in a single request and doing it very efficiently. Not just efficient, but it's efficient on storage, but efficient on the request. Okay, let's go back to slides. Whoops. All right, what did I do? Here we go. Whoa, nope. Okay, Windows 11, good times. What are we doing here? There we go. Right on. Okay. So now what we've got is we've denormalized and materialized our category name and our tag name in our product tables. So when we need to create a new product, we need to populate these additional properties. But what if I rename a category, right, or rename a tag? How do I manage that referential integrity between these containers? Well, it turns out Cosmos DB has a really good way of being able to handle that, and it's called change feed. Now, change feed is an API, and it lives within every Cosmos DB container. Well, technically, it lives within every physical partition, but let's just ignore that for the moment. It basically, for every container is really when you would use this, such that whenever data is inserted or updated into Cosmos DB, change feed picks it up and then calls a delegate, and then you listen to that delegate, and then you can do something with that data. And I'll show you how we do that here. So if we've got, in our case here, changes occur to our product category container, change feed is going to pick that up. We're going to host that in, say, I don't know, any piece of compute. Azure Functions is often used for this sort of thing, but you could host it in anything, change feed, just as long as some hosted compute. It listens to that container for the changes. It actually pulls the container, strictly speaking. If it sees a change within there, it calls the delegate, and it brings all the changes that happened since the last time it called the delegate, or the last time it called the pull on the container there. And then using that change feed in Azure Functions, you can then make a change there. So let's demo this. So what I'm going to do is I'm going to update the category name in my product category container, and then I'm going to use change feed, and I'm going to propagate that name change for that category into my product container. All right, so back to this. Here we go. All right, couple things I want to show you here. What's going on here? Okay, that's good. Must have typed something accidentally. All right. I'm going to query for products by category. Is this the one I want? Yes. Yeah. So this one here, we're going to run this function. We're going to do multiple things in this little demo, and I want to walk you through kind of each of them here. So I want to count how many products I've got in this category, and then we're going to output that within here. So we're going to run this query here. This is the category ID. We're going to do stuff too here. This is accessories, tires, and tubes. And then I'll print that out to show you how many products are in our product container here. So you can see how many products we're going to update when we update the name of this thing, this category. So here in this function, I'm going to do an update. So here's the same category ID and the category name, accessories, tires, and tubes. And I'm going to make a very simple small change here. I'm going to replace the word and with an ampersand, and then I'm going to update that back into my product category container. So here I'm just going to create a new product category object. Here's the category ID I've passed in, obviously. Type is category because that's hard-coded for this discriminator property. And then here's my updated name, accessories, tires, ampersand, tubes. And then I'm going to call this function replace item async. This is just like a read item async. It takes, well, it takes one different thing, but it takes the ID, it takes the partition key, and then it takes the updated item that you want to write back into Cosmos DB. And in that case, that's our updated product category object that we've got here. Okay, next, I want to show you change feed and what that's like. So let me go past a bunch of boilerplate code here. This is the thing I want to show you. Excuse me. I've got this product category container. So it sits on the category. And then I'm going to call this thing called get change feed build processor. Just give it a name here. And then I've got this async delegate. It's a read-only collection, so it's an IEnumerable collection here. I'm going to deserialize that as a product category object because I'm just running this on that one container, and there's only one type, entity type in there, product category, cancellation token. And then as this delegate, or as this is run and the data is passed into this delegate, I'm going to fetch each one of them that come in. So this is, I'm going to for each through this delegate, this IEnumerable, this read-only collection. I'm going to pull out the ID of the category and the category name, right? Because every change I see in here is going to be a category, product category. And then I'm going to do a task.add to my a list of task objects, and I'm going to call this update product category name a function below, and I'm going to pass the category ID and the category name. Now, let me go down further here. So I've got this other function, and what I'm going to do in here is this is the function that's getting called every time change feed happens. So if I see a new product category that's added or an updated product category, that's getting called. That function, update product category name. Now what I'm going to do in here is I'm going to run a query against my product container. So select star from C, where C category ID equals category ID, right? That should look like our product query from earlier. and then just normal kind of my query definition here. Now for every product that comes back in my response, I'm going to loop through each of those. I'm going to keep a little product count here so you can see that I'm updating the same number of products that I got in my original query where I counted them. And then I'm going to update my product.category name. So that's the category name property inside that product to my new category name. Okay, so that's where the change is being made. And then I'm going to call replace item async. That's the update function in Cosmos DB. And I'm going to persist that product back into the product container. That's where the magic, the work is happening, where the new category name is updated for every single product that I brought back through here. Okay, so that's all the code I'm going to show you in here. Here, I've got my app running, and I've got change feed processor running here below. Okay, and it's running in its own instance. Okay, so let's run it. We're going to run number E here. Is that right? Yeah. So print out the category name and the number of products. So I've got 11 products in here for accessories, tires, and tubes. And I'm going to press enter. And that's going to change. Now, if I look at the bottom here in the change feed processor, see, one change received, and it's updated 11 products with the category, updated category name, accessories, tires, ampersand, tubes. Okay, it's that easy, right? And actually, it's that fast. So now I'm going to run the query again for that category ID. And look, I've got 11 products and that category name, accessories, tires, ampersand, tubes. Okay, now if you didn't see that, let's change it back. All right, so I'm going to change it back here. Oh, did it work? There it goes. One change received, and then 11 products updated back to accessories, tires, and tubes. Okay, so there we go. So change feed used to maintain referential integrity in your containers. Okay, how are we doing? Oh boy, getting close on time. All right, let's keep trucking here. All right, so now we're on to our last entity. This is sales orders. Same process as before. We're going to put these things into JSON. And we're, of course, going to embed these things because it's a one-to-few relationship. You're not going to have an unbounded shopping cart for your sales order here. And we'll store it in its own container. We'll call that sales order. We're going to look at our operations again. So we're going to, of course, create a sales order. We want to list all sales orders for a customer. And then this other one is we want to query the top 10 customers by the number of sales orders. So let's look at this, and that's our query here, right? So select star from C, where C.customer ID equals customer A. And so we want to make this sure this is a single partition query. So we're going to use customer ID as our partition key here for our sales order customer. Now, before we go any further, I want to take a step back. Notice before, we used customer ID as the partition key on our customer container. Well, could we store customers and sales orders in the same container? Actually, the answer is yes, you can, absolutely. Not only is this technically possible, this is actually a best practice for a NoSQL type of database. This data, Cosmos, is schema agnostic, so you can take advantage of that. This is something that's totally supported. Anytime you have data that shares the same partition key and has similar access patterns like we do here, like it's normal, you would want to query a customer and their orders at the same time, then yes, this is suitable. You want to do this type of thing. And that's what we've got here is we've got customer ID as the partition key, and the access patterns are going to be very similar for this data. So instead of storing customers and sales orders in different containers, I'm going to put them in that same container. We've got to make some additional changes here. Customer, I'm going to have to add a new property. I'm going to call that customer ID. And then the other thing I'm going to do here is I'm going to change customer from ID as a partition key to customer ID. So now they have the same value for customer has the same value for ID and partition key for that document there. Okay. Next, also, I need to distinguish between these two. So I'm going to add a type property in here. I don't know what's going on with my slide. That's acting weird. But if you saw there really quickly, I had a property called type, and I've got sales. Why is it doing that? I don't know. But I've got a type property, trust me, for sales orders. That's got a type called value called sales order, and then I've got a type for customer, and that's got a value of surprise customer in there. This way, I can do queries like, well, I'll show you here in a second. But what I've got is a logical partition where I've got one customer document for logical partition, and then all their sales orders. are all going to be within that same logical partition. Here, listing sales orders for a customer. So I'm going to select start from C, where C.customer ID equals customer A, and C.type equals sales order. So I can get all the sales orders for that customer using this query. Okay, let's query sales order by customer ID here. And I got 10 minutes. I better get moving here. Okay, query sales orders by customer ID. Getting my database v4. We're on to our last one here. Customer, here's my customer ID. There's the query I was showing you earlier. Here's my query definition. Let's go ahead and run this thing. This is option F. And here we go. Printing out the orders for this customer. Here's their sales order. You can see the type there. Here's an order. It's got a bunch of stuff in there in the order details. And then here's another order here. And here you can see they just got one item in here. So that is your customer query. All right, so I've got 9 minutes. Boy, I'm really punching it close here, aren't I?
Mark,
right.
We have a question.
Yes.
When would we choose Cosmos DB over, say, storing JSON in SQL Server, or perhaps even Azure Table Storage?
Right. So yeah, you could store. I know SQL's done a good job adding JSON to that. What I will say is we still are different in that Cosmos provides an SLA on latency, whereas SQL does not. So if you have a latency sensitive, it's latent, highly sensitive applications or sensitive to latency, Cosmos may be a better choice. We also provide 5 nines of availability when you're replicating into 2 or more regions. So if availability is your game, Cosmos may be a better choice. Also, I guess you could use the hyperscale. That's a sharded SQL, is it not, Gary? Remind me, I'm not familiar with everything, but so you can shard SQL. I would just say it may come down to other things as well, but I know that those are 2 things that are different about Cosmos versus, say, SQL. Okay.
Absolutely. Thanks, Mark.
Yeah. Okay. All right. Let's keep going here. Where am I? All right. Really getting close to the end. Oh, here we go. Last thing is I want to do my top 10 customers query here by the number of sales orders. So what I need to do here is I have to count the number of sales orders for each customer and then sort those counts in descending order and then return me the top 10. Now, even though customers and sales orders sit in the same container, I can't actually write a query that will do that. The query language does not support that type of thing. So again, I'm going to denormalize my data. And what I'm going to do is I'm going to denormalize and materialize the sales order, the count of the sales order for customer, and I'm going to stick it in the customer document. So what I want to achieve is that each time I add a new sales order in here, I'm then going to increment and update the value of that sales order total for each of the customers in here. And now what I could do is I could write a query like this. So I could select top 10 from C, where C.type equals customer. Remember that discriminator property. And then I'm going to order by C.sales order count in descending order. Okay. So in this demo, I'm going to show you a bunch of stuff. I'm going to create a new sales order, and I'm going to update the sales order total. And then I'm going to do my query for my top 10 customers. Now, this is cool in that, I got 6 minutes. I know I can do this. I'm going to show you something cool is that, well, let me show you the query. So I'm going to query customers and sales order total here. Again, this is just a query. Oh, here I'm going to show, this is interesting. I'm going to do something different here. I'm going to run this query. It's going to give me back the customer and their sales orders, and I'm going to do it all in a single query. So unlike the other queries where I was deserializing data into a specific POCO or a specific object, I'm going to deserialize this into a dynamic type because I don't know what's coming back. I've got different entities coming back, and I need to deserialize these separately. So what I'm going to then do is then I've got a single customer object here, and then I've got a list of sales order types here. As I go through these things, I'm going to inspect the type. Here I'm seeing if if item.type equals customer, then deserialize that object into my customer object here. Otherwise, if it's sales order, do orders.add and then deserialize into my list of sales orders. Okay, so that's how you handle, by the way, very cool piece of code when you've got multiple entities into that. All right, so I'm going to run a query to get my customer and orders back. I'm going to show you something else that's very cool. So the nice thing about data, when it's all in the same logical partition, Cosmos does actually support transactions. I know some people don't think we do, and I know I said a lot earlier about we don't support these relational constructs around things like asset semantics and relations and foreign keys and all that stuff, but we do actually support transactions. The difference here is that we support it within the scope of a logical partition. So that data all sits, of course, on the same physical partition, which we can control and we can do in the context of a commit, right? Because it's all sitting on the same physical piece of compute. So here I'm going to create a new order, and then I'm going to update the order total. So I'm going to do a read, point read for the customer, right? Remember, that's customer ID and customer ID here. I'm going to then increment it. So I'm going to call customer.salesorderCount++. I'm going to create a new sales order. So here's my new sales order object. I'm going to add a couple of items in here. And then I'm going to use this cool piece of code or feature in our SDK called Transactional Batch. And Transactional Batch is one way you can do transactions. You can use stored procedures that are written in JavaScript. Me personally, I like doing them in here. You could support up to 100 operations inside one transactional batch. You call it off the container object, so container.create transactional batch. I'm, of course, going to pass the partition key value because these are scoped to a logical partition. And here, I'm going to do multiple things and do them in the context of a transaction. I'm going to create my new sales order, and then I'm going to update my customer ID, right? And then I'll call execute async. All right, so let me do that, and then I'll show you my query here later. This is my customer order or customer query here. Select top 10, C, first name, last name, sales order count, where C.type equals customer, order by sales order count in sending order. All right, let me go and run these things. So query for a customer and all orders, that's option G. So I've got, here's the customer object, right? So Destiny Peterson again, here's her address, password, and here's sales order count. So there's two sales orders. So I've got one sales order here and another sales order here. Okay, let's create a new order and update the order total. So I'm going to run option H here, and order created successfully. Okay, now let's query her again, G, and I should see sales order count equals 3, and there it is. There's 3. Here's our first sales order. You can see. Here's our second one, and here's our brand new one. This is the one I was showing you earlier, and you can even see here's the date. That's today. For our sales order within there. Okay, so, and why aren't you doing your thing? There we go. Okay, by the way, not only does transactional batch work when you're creating orders, it also works when you're deleting orders, because again, it's all in the context of a transaction. So if I go in and I get my customer reference and I call sales order count minus and decrement it by 1, and then call transaction batch again, I got my order ID. There's my partition key. I'm going to delete item with passing the order ID in, and then call update on my customer object here. So let's delete order I, and it's been deleted. Now let's run the query again, and here's the same customer. Sales order count is now 2 again, and here's their 2 original orders within there. Okay.
Wow, Mark, I'm impressed. We managed to get that all done in the right amount of time.
Crazy, huh?
We're right at the end of the session.
Hold on, I got one more query. Here's top 10 customers. All right, there you go. So I got my customers in here, their orders in descending order, and the request charge is just 3.27. Not too bad. Okay, so boy, really cutting it tight. So let me get back to slides because I want to show you something cool. Okay. Ran our query there. Here's kind of our near product or near final category or model here. We've got a customer container with customers and sales orders. I've got product container with products, and I've got product tags and product type category. I can actually make these even more efficient. Remember earlier, I was showing you why I'm going to use a discriminator property and that it's kind of weird looking. But what I can do is that because these things share the same partition key of type, I can merge them together in the same container, call it product meta. I can query for them this way, and I can in fact use this. This is really another best practice when you have a bunch of reference or lookup data that you don't have high concurrency on. and it may have different schemas, but if they can share this same partition key of type, and you know that you're going to have less than 20 gigs for each of them, you can create like a product meta container, throw all your reference and lookup data in there, and then manage it this way. The other nice thing is too, is now I only need one single instance of change feed to monitor the entire thing. So any data, that master data that's changed, I can then monitor it and then see, okay, what type is it? And then call the appropriate update function to go and update the data elsewhere in there. So here is then finally our final model, right? So we went from, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 tables down to 3 containers in Cosmos DB, all optimized and all can scale within our database. So I hope this was beneficial to you. I hope, you know, in our talk today, you learned about kind of the concepts and the techniques and the technology we've got available in Cosmos DB to model and partition data to be highly scalable, highly efficient, low latency for your applications. Learn some of these best practices, talked about some of the concepts around embedding and denormalizing and pre-aggregating, and then of course storing related entities in the same container, or at least in terms of being updated and read together. And then of course understanding the different technologies like transactional batch and change feed and whatnot. Here is a ton of links on cool stuff. Take a screen cap of that maybe. All the data and the demos you saw is all on GitHub. So github.com/AzureCosmosDB/CosmicWorks. You can get all the code in there, all the data. There's a data loaded in there, an ARM template to create the accounts for you. It's all there for you. We've also got this available, these concepts and this content you saw all on Microsoft Learn Labs. It's in 2 different modules. You can go and take those. We've got awesome videos, Azure, on our YouTube channel. I run a weekly podcast. You can come learn about all kinds of new stuff for Cosmos DB. We've got 33 episodes we've done so far. Lots of cool stuff in our YouTube channel for that as well. So I'll take Q&A if there's any left. I guess maybe they can't. Oh, you bought some time, so we got some extra. Hopefully people can ask questions. Please fill out an evaluation. Important to me, to how can I make this talk better? And I know important to the organizers. We have a new certification coming. If you're interested in getting certified for Cosmos DB, I think that's going to come out on November 30th. We'll have a discount for the first 300 people that sign up for the exam, producing a lot of great learning content as well that'll be available on Microsoft Learn and a bunch of all the modules and lab modules and things you can learn in there. So go get certified on Cosmos DB, get ahead of the game, and go build some great stuff. More links here. That's it. Any questions? Can they answer or ask questions, Gary?
I think we've ended the question interaction at the moment.
Okay.
But yeah, very good session, and you managed to squeeze it in there right under the wire.
It's hard when I kind of go on tangents every once in a while, so it's okay. Still streaming, no Q&A. All right, folks. Hey, you know what? If you got questions, just hit us up at AzureCosmosDB.com on Twitter. I'm monitoring that pretty much all day anyway. You can ask me questions or ask us questions there. You can hit me up on Twitter. I'm at Mark J. Brown. And you can ask me questions as well if questions come up for you. I hope you like that. I'll leave these links. Come on, go backwards. All right, where are you? Come on, go backwards. There we go. I'll leave these links up here for just a few more minutes if you want to grab them, or just take a screen cap. Probably the easiest way rather than furiously trying to write them down. Definitely encourage you to go and take a look at the repository where we've got all of the demos and samples. This is a good start if you're building a new project to learn how to use our SDK. We're a database for developers. We don't have SSMS. We don't have a GUI of any kind, really. We've got the portal, but you can't really do much in the portal. If you want to build apps, you got to use code. So fire up Visual Studio or VS Code or your editor of your choice. Download our NuGet package, or if you're a Java developer, go get a Maven jar, or whatever they call it, or NPM or Python. Anyway, go get a library or packages, start writing code, and go produce something good. And hopefully, I've given you the knowledge to model and partition for efficiency and scale. That's it, I think, for me. Thank you, everyone, for joining. I hope this was valuable to you. I hope you enjoyed past Summit, and hope to see you soon. Thank you.